Okay, so we'll solve some problem regarding week 4. So in week 4 we learned something about thermodynamic radiation. We learn about uh, Stephen Boltzmann law. One second. So what we learn about Stephen Boltzmann law, that power per unit area or unit volume, which is called as intensity, this is directly proportional to T to the power 4, where T is the temperature of the system. And to overcome this proportionality constant, we will put something here. A is sigma T to the power 4, where this sigma, this is called Stephen constant. Right. So we will use this to solve our problem. And another thing, we will use Wayne's displacement law. What's this? This is if we let's say temperature in this, and no, this is lambda and its temperature, then Wayne's displacement law says that lambda max times T is equal to some constant. So let's say this is not T, some distribution. So if we have some distribution like this, this is intensity actually, in this y-axis. So what will we see? Let's say this is for T1 temperature, and this one is for T2 temperature. So it says that lambda times T is a constant. So what does that mean? As we increase, that means that T is inversely proportional to lambda max. Right? This law means that T is inversely proportional to lambda max. That means if we increase temperature, then the lambda max, that means the wavelength at which the intensity is peaking, will decrease. That means if T1 is less than T2, then let's say name it lambda 1 for T1 and lambda 2 for T2, then what will happen? Lambda 1 will be greater than lambda 2. Let's see, I represented T1 here, so this one is lambda 1, and for T2 this is lambda 2. So as we see, as we increase the temperature, the wavelength at which the intensity peaks will decrease. That means the frequency will increase if we increase the temperature, right? As frequency is inversely proportional to lambda, so frequency will increase if we increase the temperature. That means more number of particles will have higher energy in this higher temperature state, right? You understood this, right? Okay, let's move on. Okay, we come to the first question now. The question is, if the absolute temperature of a black body is increased from T to 1.414 T, then by what factor is the total emitted power per unit area will increase? So as we saw, Stephen Boltzmann law says that this power over unit area is equal to sigma times T to the power 4, where this is Stephen constant. So initially we have temperature T, then it goes from T to 1.414 T. So let's denote this quantity as some arbitrary quantity, just R. So for temperature equal to T, let's write this as R1 will be sigma T to the power 4. Let's assume initial temperature is T1. So and T2 is 1.414 T. The temperature changes to 1.414 T. So I can write R2 as sigma T2 to the power 4, right? So but we have a relation here between T2 and T1. T2 and T1. T2 is 1.414 times T1. So I can substitute here. So this will be R2 will be sigma 1.414 T1 to the power 4. So I can take out the constant 1.414 to the power 4 sigma T1 to the power 4. Do you recognize this? Sigma T1 to the power 4 I have here. This is R1. So this will be 1.414 to the power 4 R1. So we were asked by what factor the total emitted power per unit area will be increased. That means we have R2 equal to 1.414 to the power 4 R1. So we are being asked about R2 divided by R1. This what factor the total power will be increased. That means this ratio. This is 1.414 to the power 4. Do you recognize this number? 1.414. Anyone? What is this number? This is root 2.
Root 2.
Yeah, right. So this will be root 2 to the power 4. That means it's 4. So the power will be increased by 4-fold from the initial power. So the correct answer is the first one. Okay. Coming to the second question. A black hole has temperature because you have to choose the correct answer from these options. It is hot due to the gas spinning around it. actually gas are spinning around it, but it's not impacting its temperature, it's not touching. If it engulfs the gas, hot gas, then it will impact its temperature, so it's not correct. Then the second point is it is exchanging energy with its surrounding. Yes, black holes also radiate through Hawking radiation. You know about Hawking radiation? If we have a black hole and it will have some imaginary region, we will call event horizon. Below which we can't see because light can't escape this event horizon. This is also known as Schwarzschild radius. So, in this event horizon, what happens? Vacuum, in vacuum, if there is nothing also, pair production can happen. Suddenly one electron and positron pair will pop up in space, and they annihilate and they convert it to photon like this. But this is spontaneously happens. Creation and annihilation they spontaneously happen in space. But if this happens near event horizon, what will happen if one electron is created and one positron is created near to the event horizon? The pull is so strong that the black hole will pull this positron inside it, and this electron, this will escape. So in that manner, black holes radiate. Some of its energy near to this event horizon, it will be used to pair produce particle and antiparticle pair, out of which one particle will be captured by this black hole and other one will escape. So black holes radiate like this. So this phenomena is known as Hawking radiation. So black holes do exchange energy through this. Means they are radiating. They are radiating some particle, means some energy also going with that particle. So black holes exchange energy with its surrounding. Otherwise, if a black hole engulfs a star, then also it's taking the star's energy to itself. So in that manner also black holes exchange energy. And energy exchange happens, that means black holes should have some temperature. Means it's taking heat, then it should have some temperature. By what is temperature? This is the temperature is the measure of heat in the system. So if it is taking heat from surrounding or radiating heat as particles energy, then it must have some temperature, right? And the next point is it has both an entropy and internal energy, right? So in recent development, what we found that black holes black holes surface, they encode bits. Bits means what? Bits are a tiny form of information. So in other words, entropy is equivalent to information. So in recent development, we know that black hole they store information. That means they have entropy. And again, black hole has some mass, right? Black hole are very massive, so we know they have mass. And from Einstein relation, we know mass is equivalent to energy. So black holes have energy. So if they have entropy and they have energy, then we know 1 over temperature is equal to del S over del U, where this S is entropy and U is internal energy, right? So if we have energy and entropy, then it implies that it has temperature. So the third point is also correct. The black hole has temperature because it has both entropy and internal energy. And coming to the last point, radiation from nearby and far away stars are shining on the black holes. That's not correct. Radiation from nearby and far away stars, they are shining on black hole. Means black holes means it's completely black, means its absorption coefficient is 1. So whatever it takes it absorbs efficiently, 100% efficiently. So it does not shine, it does not reflect anything. So this is not correct. So the right answers are these two. It is exchanging energy with the surrounding, and it has both entropy and internal energy. Right. Any questions on this? Okay. Then we'll move to next question. Okay. So the question is, the time required for a black hole of mass of a tennis ball to evaporate approximately. So what we show, black holes, they radiate through Hawking radiation. That means eventually they will run out of their matter inside them, and they will completely vaporize, they will completely vanish. So let's do some math and calculate what is the time period of this evaporation of a black hole. So let me check my calculations. So we know power is energy per time. So we can write this as dE over dt. So power is energy per time, and from Einstein relation we can relate it to mass, like E is mc square. So in that manner I can write this as c square dm over dt. So m is mass of black hole. Then as this power, we have power, then we can use some formula that we recently studied, that is Stephen-Boltzmann formula, that power per unit area is equal to this sigma times T to the power 4, where this sigma is Stephen constant. So we have power as c square dm over dt. So I can write this is power. So let me substitute this. So c square dm over dt by area, this is p, this is a divided by a, this should be sigma T to the power 4. But the mass is reducing, so it will eventually evaporate. So I should put a negative sign here because it's evaporating. It's like this differentiation is going, and this ratio, this value is going down, and with time this mass will decrease. So for that I am putting a negative sign here. So what we have, c square dm over dt. I can take the area to the other side, where minus sigma T to the 4 and a. Then we know black hole's temperature in it is being calculated in terms of uh, universal constants and in terms of its mass. So this temperature of a black hole is h cross CQ over 8 pi Cm. So temperature of a black hole depends inversely on the mass of the black hole, right? And on this h cross C and G, there are some proper universal constants, and we can calculate the black hole's area also in terms of black hole's mass, and it will be 16 pi G square m square divided by c to the power 4. So we can substitute this a and t here in this equation. So this will be minus sigma t is h cross CQ over 8 pi Gm to the power 4, and area, there's no space there, so area is, this is 16 pi G square m square over c to the power 4, right? We need, what do we need? Mass, because mass is a variable for us here. So let's take out all the mass terms from these constants. So this is minus sigma h cross CQ by 8 pi G to the power 4. I am taking out mass to the power 4 to out, so it will be m to the power 4, and from here we have 16 pi G square over c power 4 and square. So all these are constant except the mass term. Here we have mass square and mass to the 4 here, so I will have mass square in the denominator. So let's solve this further. I can take this mass square, this is m square, to the left hand side, so it will be m square dm over dt, and on the right hand side I will have only the constants, minus sigma by c square h cross CQ 8 pi G per 4 and this 16 pi G square over c to the power 4. These all are constants. You can see h cross is a constant, c is a constant, gravitational constant, Stephen's constant. So when we put these values, we will get a constant. Let's write this as b. So what is b? B is made up of these fundamental constants. So eventually we got a effective differential equation like m square dm over dt is equal to minus b, right? So I can take dt to the right hand side, so I will get m square dm equal to minus b dt, right? Then to get the mass of the black hole, what I have to do, I have to integrate both sides. Limit we will decide later. So it will be mq over 3 with some lower limit and upper limit equal to minus b t from some lower limit to upper limit of time. So let's assume as at t equal to 0, mass of the black hole was m0, and at t equal to time tau, the mass vanishes, means the total the black hole is totally evaporated. So with this I can write the limit of mass as lower limit is m0. Initially it was having mass m0, and finally it has mass 0 because it is completely evaporated. Evaporated at what time? Tau. So initially time was 0 and mass was m0, and at time equal to tau the mass vanishes. So putting these limits, we will have first limit is 0, so 0 minus m0 cube over 3 equal to minus b tau, right? So I can find the tau from here. Minus cancel from both the sides, so tau will be m0 cube divided by 3b. So the time period in which this black hole evaporates is m0 cube by 3b. So you have to calculate just b from this fundamental constants. See, there are this b consists of all the fundamental constants sigma, c, h cos g. So you have to put them and find the value of b. So I am not going to do it. You can do it by yourself. So what is the question? We have a tennis ball with mass 50 gram. So we have a black hole of mass of a tennis ball. Then we have to find the time period in which this tennis ball size black hole will evaporate. So I'll put this 50 gram here, 50 gram to the power cube, and 3b, b you have to calculate. So if you do this, you will get tau to be this value. See how quickly this evaporates, this tiny black hole. So this is it. This is the solution. So there is another way of solving this differential equation. If you want to calculate the mass of the black hole at a given time, you don't want to calculate the time period of this black hole, you just want to see after some time what is the mass of the black hole. So in that case, what we can do? So we have the integration as m cube divided by 3 with some limits equal to minus b t with some lower and upper limit. So let's assume at t equal to 0 time the mass of the black hole was m0, and at t equal to some time t the mass is m. So time goes from 0 to t and mass goes from m0 to m. So in this case I can put the limits. So this will be m cube over 3 minus m0 cube over 3, and this will be minus b t. So I can solve for m. 3 will go that side. So m cube minus m0 cube equal to minus 3bt. So m cube is m0 cube minus 3bt, and m is m0 cube minus 3bt to the power 1 by 3. So here we have mass of a black hole at a given time t, where this m0 is the initial mass of the black hole. And b is a constant which consists of all the fundamental constants. You can calculate it. And t is the given time. At a given time, what is the mass of the black hole? So with this formula you can calculate. So any doubt so far? No doubts? Okay. Then we will move forward. Okay. So the degeneracy pressure of an ultra relativistic particle in 3D can be written as p to the power rho to p equal to rho to the power n. What is the value of n? So how to put it? You might be remembering from the class temperature. It is proportional to density as 1/3 power of this density, right? Then pressure is some radiation pressure per unit area. This is according to Stephen Boltzmann law is sigma T to the power 4. Then I can substitute for T here, then it's not it's equal to, but I don't know the relation between T and rho now, so this P over A will be some proportional to rho to the power 1 over 3 to the power 4, so it will be proportional to rho to the power 4 over 3. This you can check from the class. I don't remember properly right now. So the answer is 4/3 now. N value is 4/3. Right. Okay. Then coming to next question. So a particular radiation cavity, a black body cavity, it has maximum of its spectral distribution of radiation power at a wavelength at 27 micrometer, which is in infrared region. So then the temperature is changed so that the total power of radiated by the cavity is going to 16 times. So we have initially power, let's say it as P1, and finally we have power P2. This P2 is now 16 times the initial power P1. Then at what wavelength does this new spectral distribution have maximum value? So initially it was radiating at lambda max equal to 27 micrometer. Then what will be the lambda max at this power P2? So as I have shown you from Wien's displacement law, that this is lambda and this is intensity. Intensity is power over area. So we will have some distribution for intensity in terms of lambda, and it is temperature dependent. If the temperature increases, the wavelength of maximum intensity will decrease, right? So lambda max means the wavelength at which the intensity peaks. So for this T2 temperature, lambda max is this one, and for T1 temperature, lambda max is this value, right? So we have to find, and this power is changed, right? So temperature is also changed from here to here. Then the maximum wavelength of intensity will also change. So what we have to do, we know the relation lambda times T is equal to constant. This is Wien's displacement law. So this lambda is maximum lambda. So we have to use this Lorentz displacement law, and we have to first find out the temperature. We have power, we know, then to find the temperature we can use Stephen's law. That is, power per unit area is equal to the sigma into T to the power 4, right? So we have initially power equal to P1 equal to sigma T1 to the power 4a, and we have power P2 which is 16 times P1. So we have P1 value, we can put it here, 16 into sigma T1 to the power 4a. So P2 also I can write P2 over area is equal to sigma T to the power 4. So P2 also I can write like this, and area I can multiply here. So P2 will be sigma T2 to the power 4 into a to the power 4a. So we can see from the both sides I can cancel sigma, and area also I can cancel. So effectively what I am getting T to the power 4 over T1 to the power 4 equal to 16. So this is I am getting from here. So I can get the relation between T2 and T1 as, I can write this 16 as 2 to the power 4, right? So this will be T2 over T1 to the power 4 is equal to 2 to the power 4. So this implies T2 over T1 equal to 2. So this implies second temperature is twice the initial temperature. I got temperature relation, right? Then it's easy to get the maximum lambda now using Lorentz displacement law. Up to this you understood, right? I was given the powers, initial power and final power, then I have to find the maximum lambda. So for that I need temperature, because of Lorentz displacement law I have a relation between lambda and T. So for that I have to calculate the final temperature from the initial power. So the final power is 16 times the initial power, and this power has a relation with temperature as T to the power 4 from Stephen's law. So from this using that law I got the final temperature as twice the initial temperature. So I can apply that, like initially we have some Lorentz displacement law, we can write lambda max times T1 equal to a. Let's write it as lambda 1 max T1 as a. So it was initially when the power was P1, and its value also given as 27 micron. Now this will be 27 micrometer, it's given. So finally I'll also have some distribution lambda max, let's denote as this as lambda 2, then lambda max to T2 will also be a. So I have a which is equal on both the equations. So I can do one thing, as the right hand sides are equal, I can equate these two equations, right? So this will be lambda max square, sorry, don't confuse it, this is square, this is 2, this is 1, this is 1. So this lambda 2 max T2 will be equal to lambda max 1 T1. So I have relation between T2 and T1. T2 is twice the value of T1, so I can put this here. So this will be lambda max 2, so this will be 2T1, and this will be lambda max 1 T1. So I can cancel T1 on both the sides. So what I will get, lambda max 2 is half of the value of lambda max 1. So lambda max 1 value I have. So you notice that as the temperature increases twice, the wavelength of maximum intensity decreases to half. So I have the value 27 micrometer. I can put it here. So it will be 27 over 2. So it will be 13.5 micrometer. So the wavelength at which the final state will radiate is 13.5 micrometer. Right. Any questions till now?
Questions?
Yes or no? So the final lambda at which the intensity will peak is 13.5 micrometer. Okay. So the answer is A. Coming to the next question. Okay. The question is maximum limit on white dwarf mass in terms of solar mass. This is a famous law you might be knowing as this Chandrasekhar limit. What is this limit? Says the mass of a white dwarf cannot exceed certain value of certain upper limit of mass. So this is at ultra relativistic limit. That means the momentum of the particles inside the stars will be very much greater than the mass of the particles. So Pc will be very greater than mc. So Chandrasekhar did this took this approximation, and he found out a maximum limit of a white dwarf star. What happens at this limit, like if a star is there, it is consists of proton, neutron and electrons, right? So these are all fermions. So we know from our previous classes, like fermions obey Pauli exclusion principle. So fermions obey Pauli exclusion principle. What does that mean? A single means one state of electron can occupy only one energy level. So inside a star there are many electrons. Let's assume the fermions as electrons. Similarly you can assume proton and neutron also. So let's assume as electrons. So these electrons, they will occupy some energy levels and they will obey Pauli exclusion principle. That means if you compare it with staircase, one marble can occupy only one step. So in that manner, so finally they will occupy all the energy levels. But if they are consist of some bosons, then what will happen? More than one particles can occupy the same energy levels. So this arrangement, uh, this decide the size of the star. That means what? Let's assume you have some 3 stairs and you have 3 marbles. So if they are fermions, you can put them 1 1 1. But so in this case, the size of the system is large, but let's assume they are bosons. So in that case I can put 3 marbles at one energy level. So in that case the size of the system will be small. So fermions like put pressure on the means this Pauli exclusion principle, it generates the pressure, degeneracy pressure. Like there are some discrete energy levels. So that means only one electron or one fermion will occupy that energy level. So eventually it will fill out, and the next marble it will try to come on this marble. Means if there are 4 marbles and you have 3 stairs, then it can't happen. Like they are already occupied. So this electron, it will try to occupy the any one of the energy state, but it can't because of Pauli exclusion principle. So it will generate some pressure in that star. So this pressure, what this pressure does, it goes outward. This pressure is exerted outward. They will try to occupy a state, but it is not allowed. So they will be repelled from each other. So due to this pressure, these particles will put a pressure towards outside the star. But the star, it has mass, right? So it has some gravitational pull. So the star has mass. So the particles in this, they will attract each other through gravitational force. So this gravitational force and this external pressure, they will balance out, and they will at some equilibrium point the star will be stable. But if you keep on adding mass to the star, then the degeneracy pressure means it will increase more and more, and the gravitational force will also increase more and more. As you add more mass to it, the degeneracy pressure will increase more, which will go outside, and the gravitational force will also increase, and whose direction is inside. But in that case, you are fighting electromagnetic force. Means this outward pressure, this is due to electromagnetism. Means one electron is repelling another electron, and that electron is going out towards the out of the star. This force is electromagnetic force, and the gravitational pull between these two particles is gravitational force. So as you might be knowing, gravity is very, very weak compared to electromagnetic force. So up to certain point they will balance, but if you keep on adding mass to the star, then at some point this electromagnetic force will dominate, and the degeneracy pressure will be more compared to the gravitational pull. So in that case, there won't be any equilibrium. The star will explode. It will go radially outward. So in that case, this white dwarf can't form. So there is a limit on mass up to which we can add to a star. So this limit is known as Chandrasekhar limit. You can check the derivation from the class. So what we calculated from the class, it's 1.435 to the times the mass of the sun. So we can have a white dwarf up to this limit. If we keep on adding to mass to the star, what will happen? It will explode. It will go to some other path. It can go to a neutron star, or it can go to a black hole, whatever. So we have a limit on this mass of a white dwarf from the Chandrasekhar limit. So you understood, in this, right? Whatever I told you so far. Or you have any doubt on that? All clear? Okay. So the correct answer is this one. You understood, right? Why this there is a upper limit for white dwarf, and this is due to the fact that electromagnetism dominates over gravitation after some mass, and this limit is known as Chandrasekhar limit. So do you have any question till now in previous problems, or shall we proceed? Okay, then I assume you all understood. Okay, coming to the next question now. So the question is, find the energy density of a black body radiation at temperature T equal to 6000 Kelvin in the range 450 to 460 nanometers. In this wavelength range, we have to find the energy density of a black body, assuming that this range is narrow, that the energy density function does not vary much over it. So we have a black body. You can assume it as a blob with hollow blob with some little tiny hole in it. So whatever goes inside it is trapped inside this blob, because this inner wall we are assuming to be very reflective, so it won't be absorbed. It will go and just bounce off the walls, and it will be trapped forever inside this blob, because the hole through which it can come out is very small. So the probability of coming out of this hole is very small. So we have a black body, and we have to find the energy density for this black body, and in the range 450 to 460. That means, what is the energy density that this black body contains? Some wavelengths between 450 to 460 nanometer. Let's imagine that through this tiny hole some light is passing with some wavelength lambda. So this wavelength means light has some wavelength, right? So we have to calculate what is the density, means how many light particles are there in the range 450 to 460 nanometer. This density, energy density means that what is the energy per unit volume um, of the system, like containing this photons or some radiation between this range 450 to 460 nanometer. So question number 7. So from class you might be knowing the intensity as a function of frequency of radiation for a black body, and in the range d nu means you have some frequency in the range nu to nu plus d nu. So what is the intensity intensity of radiation that is trapped or absorbed in that black body in the frequency range d nu. So you have some formula for that from the class, which is 8 pi h nu q over c square or cq, something like that, d nu d nu, and in the denominator it will be Planck's distribution function, which is h nu over kt minus 1. So you we have a intensity distribution in the range d nu means in the frequency range which initiates from nu and it goes to nu plus d nu, means in this small frequency range what is the intensity of radiation absorbed by the black body, or what is the intensity of radiation that is captured by the black body. So we have a formula for that, which is dependent on frequency as frequency to the power q. So we have what we have some wavelengths ranging from 450 to 460. So let's assume lambda 1 is 450 nanometer and lambda 2 is 460 nanometer, and we have a formula in terms of frequencies, and we know the relation between frequency and wavelength, which is lambda nu is constant h cross. So from this you can calculate nu 1, which will be inversely proportional to this lambda 1, and you can calculate nu 2, which will be inversely proportional to lambda 2. So let's do this. We have to find the frequencies first. Can anyone calculate and tell me what is nu 1 and nu 2? You have to just sorry, this is not h cross, this is c, speed of light. H nu is c, so you have to calculate nu 1 as c over lambda times nu is c, lambda times c lambda times nu is c, where lambda is the wavelength of that photon or radiation and nu is the frequency of that radiation. You know from Maxwell's equations that all the radiations, all the electromagnetic radiation that travel in the same speed as light. So there is a relation between the wavelength and frequency of the radiation, which relates the speed of that radiation. So using this relation, can you tell me what will be nu1? It's a quick math. See, you know, 3 into 10 to the power 8. Then put lambda value, which is also in meter. So you'll get frequency in terms of second inverse. Second inverse we call hertz. So what is this value?
It's 6.67 into 10 power 14 meter.
10 to the power
14
okay 14, not meter.
meter.
Like C has meter for
No, no.
it won't be meter. It's frequency.
Meter.
It will be second
As
inverse.
hertz. Yeah, yeah.
Yeah, second inverse or hertz.
Second is
So we have nu1 6.67 into 10 to the power 14 hertz. And can you quickly tell me nu2 value?
8.33 into 10 power 14 hertz.
8.33 into 10 to the power 14 hertz. Did you calculate it correctly?
10 power 14.
Yeah, 10 power 14.
Yeah.
8.33, right?
Yes. Sorry. 6.52.
Yes, it's not 8.33, 6.55. So we have nu1 and nu2. So let's look at the formula. I nu d nu, we have 8 by h nu q over cq or c square, I don't remember it properly, d nu over e to the power h nu over kt minus 1. So this d nu I can write as delta nu, which will be the difference in this frequencies. So this will be oh mm, okay, let's first one is more, second one is less. So I have to take the difference, nu1 minus nu2. So what is this value? Delta nu you have to just take the difference between these two. What will be this value? From 1.5 into 10 to the power 13 hertz, right? Are you getting this? 1 and 5. We are also getting this, right? Now you just have to take the differences with this. So we have d nu as 1.5 to 10 to the power 13 hertz. Then in the denominator I have to calculate this e to the power h nu over kt. But which nu I have to put here? I have two nu. Which nu I have to put here? I can do one thing. I can average them, those two, and I can put the average value of nu in this formula. So it will be e to the power h nu average over kt. So what will be the average value of nu? So I have to just add nu1 plus nu2, and I have to divide it by 2. So nu average will be, what will be the average? 6. point, so it will be 6.195
595.
595. Okay, so average value is 6.595 into 10 to the power 14 Hz. So I got new average and I got the difference in frequency. Then I have to calculate this parameter first. So I have I know the Planck's constant value H is 6.67 into 10 to the power minus 34. What is its unit? Joule into second. The same unit as angular momentum. So H I have, then another constant, Boltzmann constant. This value is 1.38 into 10 to the power minus 23 joule per Kelvin. And temperature, what is the temperature of the black body? 6000 Kelvin. So I have temperature as 6000 Kelvin. So new average also I have. Can you calculate this? H new average per kT, or you just calculate this part, then we will take it to E power.
Planck's constant is 6.626.
Okay, let's assume it's 63. Okay, 6. Okay,
Yeah,
62.
it should be 63.
Okay, so let's put it as 6.626. Put this and tell me this parameter. You just calculate the ratio first, then you can raise this ratio to e to the power. So can you quickly put this in your calculator and tell me the number? This ratio. Let me also do. To 6.594 divided by 1.38 times temperature is 6000. So I got, so this value, that's new IPG over KT, I am getting 5.3 and 10 to the power minus 3. Then I have to calculate the order. I have 10 to the minus 34 to 10 to the power 14 divided by 10 to the power minus 23 into temperature. This will be 11.3. So it's into 10 to the power 3. So it's 5.3. Are you getting this also?
Yes.
Okay. Then we have to just raise e to the power 5.3. What is this value?
200.
200. Okay.
0.33.
200.33. So if we got this, then we have everything now. Then we have to just substitute in the equation. So what is the equation? I mu G mu is 8 pi h over c square or c square.
No, it's C cube.
C cube.
Yeah.
Okay. here C cube, you just cross check it later. So C cube and nu cube d nu, this I am writing as delta nu, and this distribution e to the power that e to the power some 5.3, I got 200.33, right? So this is e to the power some those values minus 1, so this I got 200.33. this delta nu I have, what is this delta nu? Okay, I have 1.5 into 10 to the power 13. 1.5 into 13 hertz. And here I have a nu cube, which value I have to take. I am taking average value for the denominator, so I will take this nu as nu average. New average I have to take. So what is this new average? 6.595 10 to the 14. Then you have everything, put this and tell me the number. Let me do also, you do. 10 to 5 value 6.62 3 200 minus 199. So I am getting 15.335. Then order I have to calculate. X cross as order 24 minus 34. Denominator 10 to the power 8 to the power cube. Frequency cube 10 to the power 14 cube. This is 10 to the power 13 divided by, and this is calculated. So how much you are getting?
0.0133.
0.0133. Okay, let me just check. So 10 to the power minus 54, 10 to the power 29. Now it's plus. Okay. And this is 15, 13, 20, 31. Yeah, okay, 10 to the minus 3 here. This is 10 to the minus 3, so 0.013. Yeah, right. So this is energy density. So what will be the unit? Energy density means energy per unit volume. So this will be joule per meter cube. So So this is the answer. So what was the question? So we were told to find the energy density of a black body with temperature T equal to 6000 Kelvin in the range 450 to 460 nanometer. So at this temperature and in this wavelength range, we are getting this density to be around 0.0133. Right. So everything clear, right? Okay, then we'll move to next question. So the next question is, if I nu, d nu is the energy density of radiation in a black body of temperature T between frequency nu and nu plus d nu, the value of the integral. Okay, so we know I nu d nu, which is 8 pi h nu cube over c cube d nu over this Planck distribution e to the power h nu over kt minus 1. This we have. Now they are telling us to calculate lambda I nu d nu integrated from 0 to infinity. So we can do this integration from 0 to infinity. Then we have all the constants, and we are multiplying one nu here, so it will be 8 pi h nu to the power 4 divided by c cube d nu over e to the power h nu over kt minus 1. So we can do one thing, we can take all the constants to outside. So I have 8 pi h over c cube, then I have integration over nu for 4 d nu over e to the power h nu over kt minus 1 from 0 to infinity. So I have to do this integration. So it will be easy if I take this h nu divided by kt as some other parameter. So let's take h nu over kt as x. So then we can differentiate on both the sides. So d nu h over kt will be dx. So d nu will be kt over h dx. So we have d nu, and we can find nu also from this. So nu will be kt times x over h. So we have nu, we have d nu, then we have to substitute in the integration. So we have 8 pi h over c cube, then nu to the power 4, I have 0 to infinity, and let's check the limit. As nu is tending to 0, then x, what will be x? X is kt x, okay, sorry, x is h nu over kt. So it, as nu tends to 0, x also tends to 0. So lower limit will be same. Let's check up the upper limit. As nu tends to infinity, so x, as nu tends to infinity, x is also tending to infinity. So x range is also infinity. So the limit will remain the same. Now we have to substitute. So we have lambda to the power 4. Here lambda to the power 4 we have, so lambda is kt x by h, so kt x over h to the power 4 d nu we have kt over h dx, and in the denominator we are taking the whole h nu over kt as x, so we have e to the power x minus 1. So we see t is independent of this integration, we can take out all those parts, so this will be 8 by h over c cube, then I have kt by h, here I have 4 and 1 from here, so this will be to the power 5, and integration over x to the power 4 dx divided by e to the power x minus 1, and this limit goes to from 0 to infinity. So you can do this integration by parts, or you can put this in some program and it will give you some value, but in this case I'll show you some other path. I'll show you some other way of looking this integration. So in the answers we have zeta function, so this integration must be given zeta function. So let's compare this with zeta function. Let me define the zeta function as gamma function. Zeta function also have some integral form. This zeta of x is defined as integration of 0 to infinity, and x is already taken, so let me write this some other variable. Let's say this is s. Zeta of s will be x to the power s minus 1 divided by e to the power x minus 1 dx. So if we compare this integration and this integration, what is this integral value in terms of zeta function? So x to the power 4 is there, so 4. I can write x to the power 5 minus 1, so this will be s is 5 now, so this value will be zeta 5, right? So my integration will be 8 by h over c cube, then I have k t over h to the power 5, and this has zeta of 5. So let's check the options. So we have terms. Okay, we have to check it must be c square, right? It's cq we are getting, because in the answer it's c square. You can check this later. So all other parameters we can check. We have in answers temperature dependence to the power 5 and temperature to dependence to the power 4, and we have zeta functions zeta 5, zeta 4. So let's check our answers. So we are getting answers in terms of temperature to the power 5, and we are getting zeta function zeta 5, and all other constants you can calculate, and you can try to get this number. So which is matching with our answer? We have t to the power 5 here and zeta 5, so this is the correct answer. So it's done. So this is the correct answer. You got it right? So it's done. Do I have outcast? Okay, so this is the last slide. So I have time. Okay, we have half an hour more. So do you understood this question? Do you have any doubt from the previous questions or anything? We have time, so we can discuss. Or I have to find more formula and more questions and give it to you. Okay, then I assume you don't have any questions. Then you have to utilize the rest of the time doing some more problems. So let's find some more problem. So I'm giving you a problem. Okay, so it took it too much. So okay, let's find simple. Okay, you can maybe do this. Let me check. So the question is, derive the value of the constant k in Wien's displacement law what is this law? Lambda max times temperature is a constant A. So you have to find the value of A. Where this lambda max, this is the wavelength at which the spectral radiation is maximum. So this is wavelength at which the spectral is maximum. So we have Wien's displacement law. That means we have some distribution in intensity and a lambda plane, and we have lambda max here. So this is at a particular temperature T. So according to Wien's displacement law, this lambda max times temperature will be some constant always. So I have to find this A value. So let's see how to do this. Okay. So let's start from electromagnetic. For an electromagnetic wave, we have a relation lambda times the frequency will be the speed of this wave. As it is electromagnetic radiation, its velocity will be always the velocity of light. So from this I can get a relation in terms of frequency as nu is c over lambda. Then I can take d nu as d nu over d lambda times d lambda, right? Then I have to find this d nu over d lambda. So d nu over d lambda will be c minus c over lambda square. Let's write it as mod, we don't want negative sign, minus c over lambda square. So d nu will be c over lambda square d lambda. We want this way. So this is c over lambda square d lambda, right? Then we know from Planck distribution formula this intensity I knew we know. Then I have to find, sorry, it's already in I knew. Okay, we already know the intensity in terms of frequency. So as we are converting everything in wavelength, we can convert this intensity in terms of wavelength also. So this will be I lambda, this will be I can differentiate this I nu, and the dependence will be I nu times d nu over d lambda. So let's take more here also. As we did for this case, we can do for this one also. Like we know the form of I nu d nu, right? I want to find I lambda d lambda. So what I will do, d nu form I got it from here, so it will be I, as I am replacing d nu to in terms of lambda, I can write this in terms of lambda, and d nu I will write d nu over d lambda times d lambda. So this is I lambda d lambda is I, okay, so it's I nu times d nu over d lambda. So I can write this as, there's no more space, so I can write d lambda as, sorry, I lambda as I nu times d nu over d lambda. So initially I know the form of this I lambda d lambda, I nu d nu. So I want to find I lambda d lambda. So I lambda d lambda, I can substitute this d nu form as I got from here. Then I will get the intensity in terms of lambda. So this is it I got, and let me find some white space. Okay, here. So what I got, I lambda equal to I nu into d nu over d lambda. So we calculated this d nu over d lambda which will got C over lambda square, right? We calculated recently. So, and we also know I nu d nu, which will be 8 by h over c square. Let's write c square nu q d nu over e to the power h nu over kt minus 1. So, as I am writing this in terms of I lambda, I can divide this with d lambda, then I'll get this form d nu over d lambda, and then I'll have 8 pi h over c square nu q over e to the power h nu over kt minus 1 and d nu over d lambda, and this value is here, and I can substitute this lambda value as I know nu value from this relation. Lambda times nu is c, so I will get nu is c over lambda. So how much I will get? So this is I lambda. So 8 pi h over c square, I'll get lambda will come down, so c cube over lambda cube from here. Then I can do one thing here, substitute this e to the power h by lambda, then I will have hc over kt nu minus 1, and I will have from here c over lambda square. So effectively I have I lambda as 8 pi h over c square, and I have c4 here, and I have lambda to the power 5 and Planck distribution e to the power hc over kt mu minus 1. So c square c4 cancel, so effectively I have this distribution. You just check the c power. If it is cq, then we'll have c in the numerator. If it is c square, then we'll have c square in the numerator. Then what do we have to do? Okay, so we have distribution in terms of wavelength, right? And the Wien's displacement law is lambda max times t is some constant a. That means at a maximum value of lambda, this relation holds. So if lambda is maximum and we have a function in terms of lambda, so what will happen at this lambda maximum point? Its derivative will go to 0, right? If we have some function in terms of x at a saddle point or at a maxima or minima of this function, we will have df over dx equal to 0. So at lambda maximum we have will have this intensity as maximum. So the derivative of this intensity in terms of with respect to lambda will be 0, right? Then let's do the derivative. Okay, so lambda I have, if I do the derivative in terms of lambda, how much I will get. Let me take out all the constant outside first. 8 by h c square I have, depending on it is cq or c square, the c power will be determined, and I have to differentiate with respect to lambda. What I have, lambda to the power minus 5 over e to the power hc over kt. Oh, sorry, this is lambda. Kt over lambda. Lambda. So I have to do the derivative, then I have to equate it to 0. So let's apply chain rule, and this constant will go to right side, then this constant goes to 0. Effectively I have to do the derivative only. So applying chain rule, I will have minus 5 lambda to the power minus 6 divided by this term. Then I have to do the second part, lambda 5 is constant, then I have to do the derivative of this d over d lambda e to the power h c over k t lambda minus 1 to the power minus 1, and it will be equated to 0. So I have minus 5 lambda to the power minus 6, and in the denominator this term e to the power minus 1. Then I have lambda to the power 5, then doing this derivative, applying chain rule, minus 1 times e to the power this term minus 1 to the power minus 2. Then again I have to do the derivative with respect to this, so I will have hc over kt 1 over lambda. So this is minus 1 over lambda square and e to the power hc over kt lambda, and this will be equal to 0. It's too much, huh? So this is minus 5 lambda to the power minus 6 e to the power function minus 1 plus, okay, I have minus here and minus here, so plus, and I have lambda square here and lambda to the power 5, so I have lambda cube divided by, okay, I have constants here, hc over kt, then the rest of the part, e to the power hc over kt lambda, this part, and then 1 over e to the power this minus 1 square. Here we have this to the power minus 2, so in the denominator it will be square. So let's solve this. So this will be 0 at what? Lambda equal to lambda max. So in the denominator I have e to the power on this minus 1, and here I have square, I can take 1 on the right hand side and equate to 0, or I just multiply e to the power this minus 1 to the power square and the numerator and denominator, then effectively I will have e to the power this part minus 1 multiplied with minus 5 lambda to the power minus 6, then I have hc lambda cube over kt e to the power hc over kt lambda Mrs. max equal to 0. Here also I have hc over kt lambda max, right? So let's take I have lambda to the power minus 6. Okay. So I have minus 5 lambda to the power minus 6, then e to the power this minus 1. Let's take this constant as some other constant a. I don't have to write it again and again. Then a lambda to the power cube e to the power this equals to 0. So you see in this hc over kt I have taken as a, so I have hc over kt also here, so it will be a over lambda, and here also a over lambda. So what we can do then? Did I do some mistake? How I got lambda cube? Did I do any mistake during this derivative? Oh, okay. Yeah, I did mistake here. See, I did differentiation here first with respect to this lambda to the power minus 5, then I kept this as constant, then second term I have to kept this as constant, then do the derivative with this second term. I took this 10 to the power 5, it should be minus 5, so it's minus 5, so it's minus 5 divided by this lambda square, so it's minus 7, so it's minus 7 minus 7. Okay, that's no more space, so I have minus 6 minus 7. I can take 1 minus 6 common, then I'll have, let's take this minus sign inside this, then I'll have 5 into 1 minus e to the power a over lambda plus a, and I am taking 10 to the minus 6 to the right hand side, then I'll have lambda to the minus 1 here, so it is a over lambda here, and it is a e to the power a over lambda equal to 0, and this is at lambda equal to lambda max, right? Then what I So in my solution previously I am getting term without this term. So where did I do mistake? I think I didn't do mistake. Let's proceed with this. Let me find some more word space. Okay, so effectively I am getting 5 times 1 minus e to the power a over lambda times a over lambda e to the power a over lambda equal to 0 at lambda equal to lambda max, right? Five into 1 minus, okay, okay, this I have to solve. So what I have to find, okay, this will be 5 minus 5 e to the power a over lambda plus a over lambda e to the power a over lambda equal to 0. So we can't solve this like this because we have lambda 1 in the denominator and we have lambda in the exponent also, so we can't take all the lambdas in linear form. So we have to do this graphically. So in 1 minute. Okay, maybe I did some mistake. I should not be getting this term. Okay, you can check with by yourself later. So let me proceed with this. 5 into 1 minus e to the power a over lambda plus a over lambda equal to 0, lambda equal to lambda max. Then I will get a form a over lambda equal to okay, there is no mistake. I did it correct. Okay, so from this equation I can take common e to the power a lambda. So what it will be then 5, then first term will be e to the power minus a over lambda, the second term will be minus 1 plus a over lambda. I am taking common a to e to the power a lambda to the right hand side, so it will be 0, right? So this a over lambda will be, hello, so let me finish this. So a over lambda will be 5 times 1 minus u to the power minus a over lambda. So transcendentally we can solve this, so it will be 5 times some epsilon, let's assume. So graphically we have to solve this. So if we plot this function graphically, we will get this epsilon value to be 5 e to the power minus 5, which will be around 0.0337. Then you will get this value to be around 5 minus 0.30337, which is around 4.9663. So we have a equal to h cross c over kt. So let's put it. So a over lambda will be hc over lambda kt, which will be 4 this over lambda, right? So this is hc over lambda kt. So I got a over lambda equal to this much. So a over lambda is 4 this much. So this is 4 something. So from here we can take this lambda to be lambda max. Then I'll have lambda max times t equal to hc over k times this 4 something. Then when you put these values, you will get 2.89 into 10 to the minus 3 millicalorie. This is the value of A. Okay, so that's it for today.